In my last video, I talked about electromagnetic waves reflecting from the open end of a wire pair. That seemed weird because there's nothing there to reflect the waves. But exactly the same thing happens for sound waves. Sound waves can reflect from the open end of a pipe. When I blow air into this recorder, I'm actually introducing oscillations at lots of different frequencies. Most frequencies just interfere chaotically and dissipate, but at certain frequencies we have constructive interference inside the pipe, resonance, and that produces the note we hear. For this to work, we need reflections at the open end. In fact, in this case, more than 99% of the sound power is being reflected at this open hole. Why does that happen? One common answer from my engineer friends is that there's an impedance mismatch. If you don't know what impedance is, it tells you how much you need to push for a certain amount of flow, like voltage divided by current in electrical circuits, or in acoustics it might be pressure divided by fluid velocity. So let's work it out. The specific impedance inside the pipe is about 413 rails. That's the acoustic impedance of air. The specific impedance outside the pipe is also about 413 rails, the acoustic impedance of air. So where's the impedance mismatch? Well, you can define the impedances so that we have the correct reflection. We can define a bulk impedance in the pipe and a radiation impedance at the opening. That's useful, but to calculate the radiation impedance, we need to know how efficiently this opening radiates acoustic waves. And if we know that, then we already know how much is reflected. It's the part that's not radiated. So this doesn't help to explain the physics. Another approach you often see is to assume the outside is strongly tied to atmospheric pressure. But if we force the outside to exactly atmospheric pressure, that means that there's no waves out there. So by conservation of energy, the waves must be reflected 100%. Obviously that assumption doesn't work for all cases, otherwise no sound would ever reach our ears. So how do we work out how much is radiated? Let's look at the physics. Most of the time when we deal with sound, we are dealing with very small pressure disturbances compared to atmospheric pressure. For these small pressure variations, we can assume that the local change in density of the air is proportional to the pressure change. This is not a law, just a linear approximation over a small part of whatever the exact relationship is. I'm going to drop the delta from pressure as we're just going to deal with relative pressures everywhere. Next, if we consider the air to be made up of particles, if those particles are getting closer together as we go, the density must be increasing in that direction, and we can derive an expression for that. In one dimension it looks like this. I'm just outlining the steps here. If you want more detail, I'll put a link below. And thirdly, if we consider the forces on a small parcel of air, we can write down F equals ma for that parcel of air. When we solve these three equations simultaneously, we obtain what's called the wave equation. Here, the second derivative of pressure with time is related to the second derivative of pressure in space. Second derivative means rate of change of rate of change. This might not make complete sense to you, but bear with me for a moment. We can repeat the same steps for more dimensions, and we get the respective wave equation with more spatial dimensions. I'm going to use 2D in this video. From here, we're going to take this wave equation and see what the implications are. One solution is p equals 0, so if we have no waves, then we continue to have no waves, but that's not very interesting. If we introduce a disturbance, then we get a wave propagating outwards. What exactly do I mean by a disturbance? I mean some forced non-zero value. It could be from initial conditions at some initial time, it could be from the boundary values, or it could be a source inside the domain. The disturbance propagates outwards at a speed c equals 1 on square root of k, so we'll replace 1 on k in the equation with c squared, which is now how the wave equation is usually written. What about in our pipe? Let's start with a disturbance in the middle. A wave goes in each direction. Now I'm going to pause the simulation here and start with this as the initial pressure distribution. Now both peaks move in both directions. Hang on, what's gone wrong here? Surely the physics shouldn't depend on when we start the simulation. Well, because of the second derivative of time in the wave equation, we need to specify two sets of initial conditions. Just having a snapshot of pressure at one point in time is not sufficient to pin down what's going to happen. We need to specify pressure and rate of change of pressure, or pressure and particle velocity, or something equivalent. Now, if we want a wave to go in one direction, we need a very specific value of the time derivative. We need partial p partial t equals minus c partial p partial x. And if we start our simulation with that value, now the wave does propagate in one direction only. But for any other value of the time derivative partial p partial t, we have a superposition of waves travelling in both directions. Why am I telling you this? Because I want to point out that there's nothing strange about the end of the pipe, where waves end up travelling in various directions. Pressure does naturally want to propagate in all directions. What's special is when we have a unidirectional wave inside the pipe, then the wave satisfies this very special relationship. Now if we have this relationship, from that we can derive that the second derivative is like so. But that's the wave equation in one dimension. If we compare that to the 2D wave equation, then this y term must be 0. The only way this can be true everywhere is if the waves look something like this. But that's not physically possible for lots of reasons. This infinite wavefront would have infinite energy, and there's a pressure discontinuity here, which is only allowed at a boundary. Similarly, something like this is not physically possible. Again, we can't have a pressure discontinuity that's not at a boundary. We know physically what happens is diffraction, but that means that the one-dimensional wave propagation must be violated, and some of the wave must be reflected. Now let's derive the diffraction pattern and how much is reflected. This is going to get a little deep, so I'm sorry. Okay, I'm not sorry. Let's assume for a moment that the original source of these waves is a single frequency that has been going for all time. Then the resulting pressure at any point in space can only be oscillating at that frequency. We can separate the solution at any point into a spatial solution and an oscillation in time. I'm using complex exponentials as the phase might be different at each point, and complex numbers let us conveniently carry around both amplitude and phase. Now we can further decompose this solution into a sum of plane waves. What's a plane wave? It's a field in all space that looks like this, or this, or this. Regardless of what the spatial solution looks like, we can always decompose it into a sum of plane waves, using something called a Fourier transform. Now that we have that background, we can finally do the fun part and look at the radiation from the pipe. To make the solution a bit simpler, I'm going to add a wall around the pipe, usually called a baffle. You can see the solution doesn't change very much. Let's assume we know the pressure distribution on this vertical white line that crosses the pipe opening. Let's pretend, for example, that it's constant at the opening and 0 elsewhere. Then there's a unique combination of plane waves that produces that pressure distribution on the white line. How do we work it out? Well, if we take a plane wave at some angle, the values along the white line are a sinusoid of some frequency. If we take a plane wave at a different angle, that's a sinusoid of a different frequency. So if we want to know what combination of plane waves produces this overall pressure distribution on the y-axis, we need to decompose this function into sinusoids. Again, you might recognize what this is. It's a Fourier transform. And you might know that the Fourier transform of a rectangular function is a sinc function like this. How does that relate to the radiation pattern? Well, if we take a point far out here, say at 30 degrees from horizontal, and plot the phase of the various plane waves at this point, we get a graph like this. Where the phase is varying rapidly, neighbouring plane waves cancel. It's only this region where the phase varies slowly that ends up contributing to the total amplitude, which happens at 30 degrees here. In general, it's the plane waves travelling radially outwards at whichever point we choose. So this point here, which I'll call 0 degrees, maps to horizontal plane waves, which lie here at 0 frequency in the Fourier spectrum. And as we go to higher angles, we get higher spatial frequencies at the y-axis, until we get to 90 degrees. And that's the limit. Given a fixed wavelength which our source is producing, we can't make the y-axis frequency any higher than what we get pointing directly along y. So there's a cutoff here at the spatial frequency of our source, k. So what happens to the energy in the rest of this Fourier spectrum? Well, it can't be radiated at any physical angle, so it must be reflected. To express this cutoff more quantitatively, if the half-width of the pipe opening is a, then the first zero of the sinc function is at 1 over a. I'm going to rescale the bottom x-axis here by a, so that the first zero is always at 1. Now the cutoff is at ka, or 2 pi a over lambda. You can see that the critical ratio is a over lambda, or the opening size over the wavelength. If the opening is large compared to the wavelength, then the cutoff is high and radiation is efficient. If the opening is small compared to the wavelength, then the cutoff is low and we don't get much radiation. In this video, I've worked in 2 dimensions. We can do the same thing in 3 dimensions. In that case, we take the 2D Fourier transform on the plane of the pipe opening, and the cutoff is a circle in frequency space. Now there's some things I've swept under the carpet here. I'll put technical notes in the description. But fundamentally the principle is this. Freely propagating waves have a natural wavelength to be self-sustaining. I'm sure you've seen c equals f lambda, so the wavelength lambda is c over f. But close to boundaries like the pipe, the fields can vary more rapidly than that to satisfy the physical conditions imposed at those boundaries, especially if we have a narrow pipe. The rapidly varying field components can't radiate. They're just not in resonance with the universe, which requires c equals f lambda in free space. And by conservation of energy, anything that's not radiated must be reflected. I know this video has been a hard slog, thank you for watching. If you think you have a better way of explaining this that doesn't rely on Fourier optics, let me know in the comments.